The war in the Pacific was fundamentally a conflict between tradition and technology, between martial spirit and industrial logistics. As the German POWs in Texas witnessed the undeniable proof of American industrial abundance, a revelation that dissolved Nazi ideology, across the vast moonlit ocean, the Imperial Japanese Navy, the undisputed masters of night combat, were about to encounter a technological ghost that would shatter their doctrine and redefine naval warfare forever. The IJN's strategic bedrock for decades was the absolute conviction that their superior training, unmatched night vision, and lethal Long Lance torpedoes made them the masters of any engagement fought after dark. This conviction led to early, terrifying victories that cemented their arrogance, but it also masked a fatal flaw: the over-reliance on the human eye and traditional fighting concepts. For over 2 decades, following the decisive victory at the Battle of Tsushima in 1905, where torpedo boats under Admiral Togo proved the lethality of night action, night combat became the strategic spearhead of the IJN. They viewed darkness as the supreme equalizer, the means by which their finite fleet could defeat the numerically superior U.S. Navy. This supremacy was meticulously cultivated through fanatical training and precise engineering. Japanese sailors underwent grueling specialized programs to enhance their night vision, spending hours in dark rooms, observing strict diets to maintain optimal vitamin A levels, and practicing sophisticated methods of range estimation in low-light conditions. This resulted in an average Japanese lookout being able to spot ship silhouettes at 7,000 meters on a moonless night, a performance far exceeding their American counterparts. Their technological advantage lay primarily in their optical equipment, featuring world-class binoculars manufactured by Nippon Kaku, later Nikon, providing unparalleled magnification and light-gathering capability. Their offensive edge was the terrifying Type 93 Long Lance Torpedo, an oxygen-fueled weapon capable of striking targets at a phenomenal 24,000 yards, a range far beyond any distance at which American ships could visually detect them at night. This synergy between individual skill and devastating weaponry created the belief that spirit and skill were the keys to victory, leading to a catastrophic strategic arrogance. The initial phase of the war provided ample, bloody validation for this doctrine, creating a climate of fear and despair within the Allied Naval Command. At the Battle of Savo Island on August 9, 1942, Japanese cruisers executed a perfect nighttime ambush, destroying 4 heavy Allied cruisers in 33 minutes, all without losing a single ship. This swift, devastating defeat inflicted deep psychological trauma, solidifying the Japanese reputation as the Night Masters. Later, at Tassafaronga on November 30, 1942, a small Japanese destroyer squadron crippled a larger American cruiser force, torpedoing 4 ships in minutes. The Japanese High Command was confirmed in its belief: the Bushido warrior spirit, combined with night mastery, would always triumph over the rumored primitive technology of the West. This success fostered a fatal complacency, causing the Japanese to neglect serious investment in radar technology. Despite inventing the Yagi antenna in 1926 and developing the concept behind the critical cavity magnetron, internal bureaucratic inertia and a conservative naval leadership caused these innovations to be sidelined. Conversely, the U.S. embraced the British magnetron and rapidly weaponized it through mass industrial production, establishing the MIT Radiation Laboratory in November 1940, which would grow to nearly 4,000 employees by 1943. This laboratory became the epicenter of a technological revolution, a revolution built on the very principles Japan had ignored: mass production and continuous refinement of electronics. The arrogance of tradition met the shock of technological reality on the night of November 13, 1942, in the perilous waters off Guadalcanal, a locale soon dubbed Iron Bottom Sound. This was the night the mathematical certainty of American industrial technology was deployed against the human factor in Japanese combat doctrine. Commander Tamichi Hara, standing on the bridge of the destroyer Amakadze, watched in disbelief as American shells fell accurately around his ship in the deep darkness. This occurrence directly contradicted 20 years of Japanese naval belief. Hara observed American ships firing with devastating mechanical precision at ranges exceeding 10,000 yards, distances at which his highly trained lookouts could barely spot a distant muzzle flash. He was struck by a terrifying realization. The American shells arrived with perfect accuracy, yet no searchlights gave away the enemy's positions. No star shells preceded their salvos. The American attack originated from an impenetrable sanctuary of invisibility, rendering all human night vision training obsolete. The terror intensified as the magnificent Japanese battleship He, the pride of the fleet and veteran of Pearl Harbor, began to shudder under a heavy, concentrated bombardment from enemies her lookouts could not see. She absorbed 85 shell hits in darkness and rain squalls that should have provided concealment, her bridge wrecked and her steering destroyed. She was being systematically destroyed by invisible forces firing beyond visual range. When Hara desperately risked activating his own searchlights to pinpoint the attackers, the radar-directed 6-inch cells of the American cruiser USS Helena instantly found the Yamakadze, inflicting crippling damage and casualties, killing 43 crew members. The He, rendered helpless, was scuttled the following day, marking the first Japanese battleship lost in the war. This loss was not due to superior seamanship or surprise, it was due to a technology gap that redefined the rules of engagement. The truth, unknown to any Japanese officer that night, was that they were facing the newly deployed American SG surface radar. This technology rushed into mass production using the British cavity magnetron, an invention historian James Finney Baxter III famously deemed the most valuable cargo ever brought to our shores, represented a quantitative leap over any existing primitive radar systems. The SG radar operated on a highly efficient 10-centimeter wavelength, 3 gigahertz, with 50 kilowatts of output power, capable of detecting a destroyer at 15 nautical miles and tracking it with precision blind fire accuracy at 10 miles, boasting a range accuracy of plus or minus 40 yards and bearing accuracy of plus or minus 0.5 degrees. This system was integrated perfectly with the Mark 37 fire control system, utilizing an analog computer that could calculate instantaneous firing solutions, automatically compensating for target speed, course, wind, and the vessel's movement. Critically, it featured the plan position indicator screen, offering a map-like panoramic view, a vast improvement over the primitive, confusing A-scope displays used by the few Japanese radar systems. This capability allowed American operators to distinguish between ship types, track torpedo wakes, and even spot periscope-depth submarines, working equally well in daylight and night, clear weather, and storms.
The realization within the Japanese command structure that the enemy was fighting from beyond visual range signaled not just a tactical defeat, but a cultural catastrophe. For the Imperial Japanese Navy, rooted in samurai tradition and the premise of individual combat excellence, the radar revolution contradicted fundamental Japanese military philosophy. Their ideology had long preached that spiritual superiority, Bushido, could overcome material disadvantage. Now, this deeply held belief was being shattered by oscilloscopes and magnetrons. Young Japanese officers raised on tales of valor struggled to comprehend warfare where the enemy was unreachable and invisible, rendering courage and personal skill meaningless. The Japanese response to this emerging crisis was tragically hampered by systemic and organizational deficiencies. Japan had actually developed its own cavity magnetrons by 1937, years before the British device was shipped to the US, and Dr. Hidetsugu Yagi had invented the directional antenna that now bore his name in 1926. Yet military leadership excluded Yagi from radar work due to a lack of vision, and tragically, inter-service rivalry prevented any coordination. Both the Army and Navy developed separate, incompatible systems, ensuring that whatever limited resources were spent were utterly wasted. When Japanese forces later captured British radar equipment featuring Yagi antennas, they were completely unaware the design referred to a Japanese invention. This institutional blindness and rivalry meant that their most functional radar set, the Type 22, operated at a low 150 MHz with only 2 kilowatts peak power, detecting destroyers at a maximum of 10 nautical miles under optimal conditions, with crippling inaccuracies in range plus or minus 300 yards and bearing plus or minus 5 degrees. Weighing 2,200 pounds and having a dreadful operational availability of only 40%, the Type 22 was both unreliable and cumbersome. The comparison to the American SG radar, which was reliable, light, 1,000 pounds, and possessed 95% operational availability, highlights the industrial and scientific gulf. Of the first 60 Type 22 sets built, only about 6 actually worked. Total Japanese radar production during the entire war reached only about 300 units, less than a third of the American SG production alone, a disparity exceeding 50-1 in crucial areas. The MIT Radiation Laboratory, established in November 1940 under Dr. Lee Dubridge, was the technological engine behind this dominance. Its growth to nearly 4,000 employees by 1943 underscores the American commitment to scientific mobilization. The lab's work extended far beyond the SG radar, developing over 100 different microwave systems worth $1.5 billion in production, the foundation of which was the British magnetron. This single device, producing 1 kilowatt at 10 centimeter wavelength, was 100 times more powerful than existing American technology. The genius of the American war effort was not just in inventing, but in taking the British invention and mass-producing what the Japanese could not replicate. 9 radiation laboratory staff members would later win Nobel Prizes, but their true wartime contribution was enabling the electronic revolution that transformed naval combat from visual engagement to radar-directed warfare, permanently ending the age of relying on human eyes and warrior tradition. The waters around Guadalcanal, forever marked as Iron Bottom Sound, became the laboratory where radar warfare was perfected, documenting the IJN's escalating losses in night engagements, losses that tripled American figures by early 1943. The IJN, having entered the war as masters of the night, ended it unable to venture out after dark, defeated by technology that didn't exist when their training began. The SG radar's revolutionary sight was only half the equation. Its lethality required a platform capable of utilizing its newfound vision with ruthless efficiency and, critically, in overwhelming numbers. That platform was the Fletcher-class destroyer, a masterpiece of American standardized design and relentless mass production. The Fletcher was not a vessel of aesthetic beauty or traditional naval grandeur. It was a pragmatic, versatile, and lethally well-equipped workhorse, specifically engineered for the vast, attrition-heavy demands of the Pacific theater. Its sudden, overwhelming emergence in the fleet delivered the second, equally devastating blow to the Japanese naval strategy, attacking their core doctrine of qualitative superiority with an unanswerable flood of quantity and precision. By 1943, the Imperial Japanese Navy was sinking under the immense weight of attrition. They struggled immensely to replace losses, often resorting to smaller, less effective destroyer designs like the Yugumo and Akizuki classes. While these were excellent designs in their own right, they suffered from cripplingly slow production rates and a chronic lack of standardized, reliable equipment due to Japan's fragile industrial infrastructure. Japan's industry was highly decentralized, reliant on a brittle supply chain, and susceptible to bottlenecks, a model utterly incapable of matching the standardized rapid output of American shipyards. The U.S., however, launched a destroyer construction program of unmatched scale. Between 1942 and 1944, 175 Fletcher-class destroyers were launched, a construction feat that had no contemporary equal. This sheer overwhelming quantity meant that for every Japanese destroyer lost to combat or accident, the USN could deploy an entire new squadron or even flotilla. This capability was the industrial mathematics of defeat, a reality that the skill and courage of individual Japanese sailors could never overcome. The Fletcher was built in 7 different American shipyards, using prefabricated sections that were welded together in assembly line fashion, process that streamlined production and ensured absolute interchangeability of parts, further emphasizing the American industrial advantage over the decentralized Japanese system. The Fletcher-class represented a quantum leap in American destroyer design, abandoning the structural weaknesses of earlier ships for a continuous flush deck that provided superior strength, improved crew habitability, and critically, massive internal space for the voluminous electronic equipment necessary for radar and fire control systems. Their versatility was the key to their dominance. Firepower. They were armed with 5 5-inch 38-caliber dual-purpose guns. This was arguably the finest medium-caliber naval weapon of the war, capable of a blistering rate of fire, up to 22 rounds per minute, making it equally effective and terrifying against surface ships, submarines, and high-speed aircraft. This dual-purpose capability meant the Fletcher was never strategically compromised, able to simultaneously engage surface targets and defend against air attack. Speed and endurance. Capable of speeds exceeding 35 knots, over 40 miles per hour, they possessed the fuel and supply endurance, a range of over 6,500 nautical miles at 15 knots, a one of over 6,500 nautical miles at 15 knots, ensuring constant fleet coverage. This endurance was vital for sustaining the relentless operations across the immense
electronic
Pacific
core.
distances.
The Fletcher was not merely a gun platform. It was designed from the keel up as an integrated weapons system, configured to carry multiple, sophisticated radar sets, centered around the SG surface search radar and the fully automated Mark 37 fire control system. The Mark 37, often housed in a dedicated director atop the superstructure, combined input from the radar and optical sights with a specialized analog computer to calculate precise firing solutions in real time, delivering a level of accuracy the Japanese could only dream of. When the Fletcher combined its rapid-fire ordnance with the mechanical, digital precision of the SG radar, it was transformed into the ultimate iron surgeon, a ship that could perform precision strikes in the pitch dark that the Japanese, relying on optics and instinct, could not even begin to counter. The destroyer, traditionally a small defensive escort vessel, was thus weaponized into an independent, devastating offensive unit, able to hunt and kill Japanese cruisers and even capital ships with alarming regularity, a task previously reserved for heavy cruisers. The Fletcher's heavy torpedo armament, initially 10 21-inch torpedo tubes in 2 quintuple mounts, was equally radar-directed, allowing them to utilize the Long Lance's own vulnerability, the American ability to fire first, against the IJN. The Japanese relied heavily on high-speed nighttime supply runs, infamously known as the Tokyo Express, to keep their forward garrisons, most famously at Guadalcanal, supplied with food, troops, and ammunition. These runs were meticulously planned to exploit the presumed Allied inability to fight effectively at night. However, the mass introduction of the radar-equipped Fletcher destroyers instantaneously flipped the tactical table, turning the Tokyo Express from a tactical lifeline into a tactical shooting gallery for the Americans. The Fletchers would lie in wait, completely invisible and undetected by the superior Japanese lookouts. The SG radar operators would track the Japanese ships approaching at high speed, providing a continuous, high-fidelity plot to the fire control center. By the time the Japanese destroyers finally came into the lethal zone, or, more accurately, when they became visible on the radar screen, they were already within lethal firing distance, and the American guns were pre-sighted, locked onto the coordinates, and ready to unleash a coordinated barrage. The American radar-directed guns often achieved the first hit before the Japanese could even identify the direction of the threat. Battles like Vella Gulf, August 6 through 7, 1943, provided the clearest demonstration of this complete reversal of fortune. The American destroyers, led by the USS Dunlop and USS Stack, detected the Japanese convoy at over 20,000 yards.
The Americans fired their radar-directed torpedoes first, sinking 3 Japanese destroyers and suffering minimal damage to themselves. The Japanese, caught completely by surprise and blinded by the darkness they thought was their ally, were unable to effectively locate the enemy or coordinate a counterattack. It was not a fair fight. It was a technological ambush, a surgical demonstration of industrial dominance. The night, once the IJN's greatest friend and protector, had unequivocally become its most dangerous, fatal enemy. The technological superiority embodied by the SG radar and the Fletcher-class led to predictable yet devastating tactical results. However, the ultimate undoing of the Imperial Japanese Navy was not just the technology gap itself, but the Japanese High Command's profound psychological and ideological denial of the problem. This denial resulted in catastrophic operational decisions and an enormous unnecessary human cost. In the face of mounting inexplicable night losses, the Japanese military leadership, steeped in the rigid doctrines of Bushido and convinced of their spiritual superiority, refused to accept that American technology could be functionally superior to their own highly trained human crews and world-class optics. The prevailing mindset, rooted in 20 years of night victory, was that the enemy's success must be due to luck, cowardice, or the failure of individual Japanese commanders. This institutional refusal to acknowledge the decisive role of radar became a bureaucratic death sentence for thousands of highly skilled sailors. The senior command often preferred explanations rooted in human failure rather than accepting that the American industrial system had rendered their core doctrine obsolete. Japanese post-action reports from the early radar battles, such as the fierce November 1942 naval engagements, frequently use the chilling terms blind fire or phantom attack to describe the American precision. They simply could not reconcile the American accuracy with their own inability to visually locate the attackers. Some high-ranking officers hypothesized that the Americans must be using massive, unsustainable arrays of flares or searchlights, which the Americans intentionally avoided, or that they had deployed submarines for detailed spot reporting in forward positions. The idea that the enemy possessed a reliable, small-scale shipboard electronic device capable of delivering accurate surface target data over 10 miles integrated into the fire control system was dismissed as pure fantasy, science fiction, or propaganda designed to demoralize the Japanese fleet. This entrenched denial fundamentally dictated their counter-strategy. Instead of halting high-risk night operations or diverting all available resources into developing and mass-producing their own effective microwave radar, the IJN instead doubled down on their traditional strengths. They intensified night combat training, emphasizing the use of the Long Lance Torpedo, and developed increasingly desperate plans to force the Americans into extremely close-range engagements where the torpedo's devastating power could be brought to bear. This desperate gambit, trying to force a close-quarters brawl, only played directly into the strengths of the radar-equipped Fletchers and their rapid-fire 5-inch guns, which could put dozens of shells onto the target before the torpedoes could arm or launch.
Final definitive proof of technological annihilation came at the Battle of Vella, October 6th to 7th, 1943. This engagement was a perfect textbook demonstration of the SG radar's tactical supremacy and the IJN's crippling vulnerability. 3 Japanese destroyers were attempting an evacuation run, the ultimate objective of the Tokyo Express, when they were intercepted by 6 American destroyers. The American force, completely unseen and operating based on their superior radar plots, was already perfectly positioned. They opened fire on the Japanese destroyers from over 10,000 yards, well outside the effective visual range of the Japanese lookouts. The Japanese had virtually no response. Their attempts to launch the vaunted Long Lance torpedoes were thwarted by the rapid, accurate American gunfire, which crippled the Japanese vessels before they could close the distance required for an effective torpedo attack. The American radar, which provided continuous, high-fidelity tracking, allowed the U.S. ships to execute immediate defensive maneuvers, easily evading the few Japanese torpedoes that were launched blindly or inaccurately. In stark contrast to the Japanese performance, the American torpedoes were launched based on precise radar data, often crippling their targets. The result was a catastrophic loss for the IJN. 2 Japanese destroyers, Yugumo and Kazegumo, were sunk, and another, Shigure, was severely damaged. The Americans lost only 1 destroyer, the USS Chevalier, which was fatally damaged not by an enemy torpedo, but by the U.S. destroyer USS O'Bannon in a chaotic post-engagement maneuver, a testament to the fact that the main Japanese threat had been neutralized by technology. The battle sealed the fate of the Japanese Naval Command's night-fighting doctrine and proved that the USN did not need superior seamanship. They had the numbers and the technology to turn every night engagement into an automated, calculated slaughter. The human cost of this technological denial was immense and strategically irreplaceable. The Japanese Navy bled out its most highly trained, skilled sailors and officers in these doomed night actions. These were the veteran commanders, the highly specialized engineers, and the experienced lookouts, the human capital that required years to cultivate, who were being systematically destroyed. The American system, rooted in mass production and standardization, could replace a Fletcher and train a proficient radar operator far faster than the Japanese could train a veteran captain or replace an entire destroyer. This disparity created a vicious, accelerating cycle of defeat. As the IJN lost its most experienced personnel, the quality of its subsequent crews plummeted dramatically, leading to operational errors even during daylight. Meanwhile, the American sailors, guided by the precision of the SG radar, gained experience and confidence with every successful night engagement, widening the skill gap further. The IJN's ideological denial meant they continued to send their best men into battles where the technological deck was fatally stacked against them. The war was lost not just on the radar screen, but in the stubborn refusal of the high command to believe the evidence of their own crippling losses and to embrace the technological reality of the modern era. While the Imperial Japanese Navy was losing its elite crews to radar-guided American gunfire, the ultimate strategic failure lay in the utter inability of the Japanese industrial and scientific base to replicate or even comprehend the rapid pace of technological innovation in the United States. This systemic failure ensured that the gap between the two navies would not just remain wide, but would accelerate into an unbridgeable chasm. The key to the American electronic dominance, the cavity magnetron, was an invention Japan actually possessed the underlying theoretical knowledge for, having developed similar concepts in 1937. Yet, while the U.S. successfully industrialized this tiny, powerful tube into the mass-produced SG radar, operating on the efficient 10-centimeter wavelength, Japan struggled with primitive, low-frequency technology. Japan's best attempts at operational radar, such as the Type 22 set, operated on a much longer wavelength and lacked the crucial plan position indicator screen. This distinction was critical. The Japanese screen was often a confusing A-scope, displaying targets as mere spikes on a horizontal line, requiring complex manual interpretation to determine accurate bearing and range. The American PPI screen, however, provided an intuitive map-like display, making radar operations dramatically simpler, faster, and more accurate, even for moderately trained personnel. The fundamental difference lay not in basic science, but in industrial capacity and organization. The American war machine was centralized and optimized for mass output, while the Japanese system was plagued by deep structural flaws. Decentralization and rivalry. Japanese military research and development were notoriously fractured. The Imperial Japanese Army and Navy maintained separate, often hostile research facilities, deliberately refusing to share breakthroughs or standardize equipment. This institutional friction meant limited national resources were wasted on redundant, competing projects, preventing the centralized focus required for a complex, capital-intensive technology like microwave radar. Material scarcity. As the war progressed, Japan faced debilitating shortages of key strategic materials, including high-quality copper, aluminum, and the specialized vacuum tubes required for advanced electronics.
American industry, operating in a resource surplus, was producing these components in massive quantities. The difference in manufacturing quality was often stark. American radar sets were robust and reliable, boasting 95% operational availability. Japanese sets, however, due to poor materials and construction, were often temperamental, breaking down frequently and achieving operational availability sometimes as low as 40%. The production gap. When the Japanese finally managed to develop a partially functional surface search radar, the Type 22, they lacked the industrial machinery and standardized processes to produce it in the necessary quantities. The IJN installed radar only on a fraction of her ships, and the process was slow and laborious, often requiring weeks of work. Total Japanese radar production during the entire war reached only about 300 units. The USN, by stark contrast, treated radar as standard equipment, installing the SG set on every new destroyer, cruiser, and battleship, often retrofitting older vessels in a matter of days. The production of the SG alone reached approximately 1,000 units, demonstrating a disparity exceeding 50-to-1 in crucial electronic warfare capabilities by 1944. This mass deployment meant that by mid-1943, nearly every American naval vessel could see in the dark, effectively turning the entire U.S. fleet into an
industrial reality amplified this disparity into a complete strategic failure. The shipyard paradox. While Japanese shipyards labored for months, facing material and labor shortages to build or repair a single cruiser or carrier, the U.S. was churning out Fletcher-class destroyers, 175 built, and the colossal Essex-class carriers, 24 built during the war, at speeds that dwarfed any Japanese effort. The Essex carrier, which formed the core of the Fast Carrier Task Force, was a 27,000-ton Leviathan that represented the ultimate expression of American industrial mobilization, capable of launching and recovering nearly 100 aircraft. The ability of the U.S. to sustain battle damage repair and continue building major warships meant that the IJN was perpetually facing a growing, not shrinking enemy force. Ammunition and logistics. The American fleet was backed by a massive, uninterrupted flow of ammunition, fuel, and supplies, managed by a logistical system that the Japanese, focused on short-range doctrine, never developed. The Fletchers could expend their 5-inch shells freely, knowing immediate replenishment was guaranteed. The IJN, fighting with increasingly desperate logistical struggles, had to conserve every shot and every gallon of oil. The radar allowed the Americans to achieve lethal hits with fewer rounds, further tilting the efficiency balance and minimizing American logistical waste. The constant American radar presence also choked off Japanese supply lines, starving garrisons and forcing high-risk evacuation runs that played directly into the USN's hands. The ultimate strategic failure of the IJN was their inability to transition from a doctrine based on quality, elite training, the Long Lance, to a doctrine based on quantity and technology, mass production, radar integration. The radar battles of Guadalcanal and Vella Gulf proved definitively that the highest level of human skill was utterly irrelevant when the enemy could calculate, track, and shoot from a range the eye could not register. The Japanese strategy of using night combat as a tactical equalizer was violently reversed. Night became the amplifier of American technological superiority, turning the IJN's greatest strength into its fatal vulnerability. The image of the sleek, functional Fletcher-class destroyer steaming confidently in the dark, its radar antenna sweeping the horizon with clinical precision, serves as the final, poignant epitaph for the Imperial Japanese Navy. The war in the Pacific was not merely won by ships or planes, but by the American ability to take complex scientific inventions, the cavity magnetron, mass-produce them perfectly, and integrate them into a standardized, massive platform, the Fletcher, ultimately converting abstract industrial capacity into devastating tactical reality. The loss of the Nightmasters was not just a military defeat, it was the ultimate strategic confirmation that in 20th century warfare, industrial might, technological innovation, and logistical standardization would triumph over national spirit and traditional martial skill every single time. The fate of the Imperial Japanese Navy was sealed not by the first bullet fired, but by the first radar-guided shell that screamed out of the darkness, striking a target that never saw it coming, ending the age of optical naval combat forever. The industrial reality amplified this disparity into a complete strategic failure.